Okay, let's talk some chemistry. As a biologist, this is my least favorite topic. So I'm not trying to make us chem majors, I'm just trying to give you enough chemistry to get through the biology. So if you're in a chemistry class, you'll find this is pretty watered down. Why do we even care about chemistry? Well, of course, our entire body is made of chemistry. It's made of chemicals. We're dependent upon those chemicals to feed ourselves and do a bazillion other things. So these chemical reactions take place every second of every day, and especially as we get into the physiology, we will see that it's pure chemistry. Also, to maintain our homeostasis, which is the #1 idea of physiology, we got to have chemistry. And to be able to talk about big things like organs and cells, we have to know what makes them up. So, if you refer back to this levels of structural organization that we had in the first chapter, chemicals become cells, cells become tissues, tissues become organs, organs become organ systems, and organ systems become individuals or organisms. So we're way back at the beginning with talking about the chemicals. So in order to get to cells, we got to know what cells are made of. So we're going to have subatomic particles, atoms, and molecules. But first of all, the definition of matter. Now, I'm not trying to make us chem majors at all. In fact, I don't want to teach chemistry ever. But I'm not going to have this definition on your test, but I may use the term matter. Matter is anything that has weight and takes up space. And it's made of elements. So, your desk is matter, you're matter, I'm matter, your drink is matter. And this, as this t-shirt says here, solid, liquid, gas, they all matter. Nerd humor. But it's true. Everything is matter. And everything's made up of elements. So, an element is fundamental substances that cannot be broken down into simpler material. Basically, I think of elements like Legos. When I was a kid, my mom bought me a Lego set, and I used to build Lego hospitals, Lego schools, Lego cars. Everything was Legos. And at the end of the day, she would come home and go, "That's nice, Amanda, but it's time to clean up." And I was always upset to tear my Legos down. But the point is, I could tear my Lego school down into its individual Legos. So those would be elements. So there's about 116 known elements. You've probably seen the periodic table in some science class at some point. It is organized to show similarities and differences between the elements, but we don't really care about that because this isn't chemistry. They use symbols to define the elements, and the point of it is, again, you can't break them down. So gold is an element. You can break gold down into gold. Silver is an element. You can break silver down into silver. Carbon is an element. You can break carbon down into. But really, the 4 elements that we're the most concerned with in the beginning of this class is what makes up 95% of our body. Carbon, hydrogen, oxygen, and nitrogen. Which really, as we saw in the first unit, the majority of your body weight being water, it's of course the hydrogen and oxygen that really make up most of it. Back to this picture, it says they need to fill these shells in order to react. With atoms, we are definitely going to judge a book by its cover. So we only really care for this class about the energy shells. Well, if I pack in a bunch of green things, that's not changing my cover. This is like adding pages to a book. If I'm just looking at the cover, I wouldn't know if the book is 500 pages or 5,000 pages. So it doesn't the way these chemically react. But again, we'll get to that eventually. Some isotopes are radioactive. This basically means that they get so many neutrons in there, in that nucleus, that it becomes very unstable. And so to stabilize, it starts to break down. It starts to try to drop some of that dead weight. And it releases energy or particles, which is what we call radioactivity. So if you look at this picture, this just shows hydrogen, and it shows the different neutrons. So we just need to see the protons are pink, the neutrons are gray. We just need to see that we have the same number of protons. The only difference in these 3 pictures, and we have the same number of electrons, the only difference in these 3 pictures is these gray dots. So we've packed on a bunch of neutrons, which changes the weight, but we did not change that orbital. We did not change the atomic number. Therefore, to the body, you wouldn't know the difference. Your body's going to judge a book by its cover. All it's going to care about is that one blue circle there. So your body wouldn't know the difference between these 3. So radioisotopes are atoms that undergo spontaneous decay. As they're trying to stabilize, they emit energy, which is radioactive. So heavier isotopes have very unstable nuclei. Their nuclei start to disintegrate. As they do this, they release rays of energy, alpha, beta, and gamma rays. We can take advantage of this in medicine. A great example of this is in the thyroid gland. Now again, at this point in this class, all you need to know is what an isotope is. But we are going to be talking about the thyroid gland a lot in AMP1 and AMP2, so I just prefer to actually use a real medical example. So if you take iodine 127 and iodine 131, the difference is iodine 127 is normal iodine that you get in your diet. If you eat a lot of salt, if you've ever noticed on the salt packet, it says iodinized salt. It just means salt that has iodine in it, as opposed to radioactive iodine. Now, your body only looks at that outer orbital, so your body's not going to know the difference between these two. But in order for the thyroid gland to make its hormones, and I've listed the hormones here, you don't need to know them at this point, we'll learn them eventually, but the thyroid gland is found right on top of your trachea, which is your windpipe. And in order for the thyroid to do its job, and it does a lot for the body, in order for the thyroid to do its job, it has to have iodine. So if you're worried that your thyroid gland isn't working well, and this is a huge concern for women, if you're worried your thyroid gland isn't functioning, they can do a test where they inject you with radioactive iodine, and if your thyroid is happy, it will absorb the radioactive iodine and do its thing, make its hormones, which means under a scan, your thyroid gland would glow. However, if your thyroid gland is not happy, it's not going to take that radioactive iodine into itself and do its thing, so the thyroid gland wouldn't glow. So it's kind of like a sneaky backwards way of checking to see if your thyroid gland is active, is seeing whether or not it absorbs the iodine. If you've ever heard of the term goiter, a goiter is a very attractive giant growth that's on the neck. In fact, you could Google image it if you want to see it. But that is from usually a thyroid problem, and it's usually a lack of iodine in the diet. So back when we first settled this country and we were living on the East Coast, our soil had plenty of iodine in it. So we didn't have goiter. But when we started to move west, some of that soil was very poor in iodine, and people started getting these giant goiters. That's when we decided to start adding it to the one thing Americans eat a lot of, and that's salt. So we started adding iodine to salt to keep us all from getting goiter, just like we started adding fluoride to our water to keep our teeth strong. But again, at this point, we just need to know what isotopes are. But another application is in the process of killing cancer cells. We can use radiation. So cells that divide like crazy are very sensitive to radiation. So that's, the definition of a tumor or cancer is when cells are kind of dividing uncontrollably. So we can blast those tumors or that abnormal tissue with radiation. So this is again just another function of a radioactive isotope. Okay, our next definition, molecules. So we just had atoms. A molecule is when two or more atoms get together. Simple as that. There's two kinds of formulas we can look at. Think of it like cooking. When you look at a recipe, often there's a list of ingredients, and then there's a list of the order of how you should proceed. It's not enough just to have the ingredients, just like it's not enough just to have the list of how you make whatever you're making, that cake or whatnot. You need both. So in chemistry, we have the molecular formula and the structural formula. The molecular formula is your list of ingredients. It tells you the number and types of atoms. So this molecule here is a very important molecule for our body. This is glucose, which is our blood sugar. So it's C6H12O6. This tells me 6 carbons, 12 hydrogens, 6 oxygens, just like a recipe that would say 3 cups of sugar, 2 cups of flour, etc. So this second example, H2, tells me 2 hydrogen ions. The third example here is H2O, which is water. How many hydrogen ions is that? Atoms, I'm sorry. How many hydrogen atoms is that? Think about it. It would be 2. How many oxygen atoms? It would be 1. Now, if I put a 2 in front, this is like doubling a recipe. So this one's a little trickier. So the number of hydrogen atoms would be 4, and the number of oxygen would be 2, because you're multiplying the 2 across to the oxygen as well. A compound is a term I'm not that concerned with. The difference is basically a molecule that has 2 atoms of different elements. So technically water is a compound because you have a mixture of hydrogen and oxygen. But again, for me, molecules are molecules. So a molecule is 2 or more atoms, same or different element for me. We won't really worry about the term. The structural formula then is like the recipe that tells you the order. When I was in home ec, I forgot to put the flour in the cookies. Yeah, those of you that bake, you realize that doesn't end so well. And so I ended up with these crusty, horrible, awful cookies. It's not like when I pulled those crusty cookies out, I could add flour at that moment. It was way too late for that. So the order of how you do things is just as important as the ingredients. So the structural formula tells us where these things are located, because otherwise I could have hydrogen, hydrogen, oxygen, and that wouldn't be water. Water is structurally, the oxygen is in the middle, the hydrogen shoots off of both ends.